This is segment 3 of lecture 1. We will address first concepts in risk assessment. These are concepts that we'll need during the entire course. First of all, what is risk? For us, we will address risk as the chance of a harmful impact on human or ecological receptors from exposure to a stressor. A stressor can be characterized by many things. For us, in our course, these will be chemicals that induce an adverse response, either in human or ecological receptors. There are many types of risks. Financial risks, risk when you're flying, risk when you're driving, radiological risks. These are important risks, but this course will focus only on chemical exposure risks. Chemical risk on itself can be caused by direct emissions to water bodies, to soil, or to the atmosphere. Our work will focus on emissions to air. Once it goes to air, humans can breathe, or there'll be deposition of particles and other chemicals, vapors even, on surfaces. Of the air risks, there are two types. Short-term risks caused by explosions, by fire, accidental releases, highly toxic chemicals on a large tank ruptures. Humans are exposed to all those chemicals. This is not the type of risk assessment we will address here in this course. We do have courses for that, and we are addressing only the long-term risks. Long-term exposure could be in terms of many years of low concentrations, low deposition rates on surfaces, on water bodies, on soils. And we are addressing not the nuisance of the long-term exposure, but only cancer risks and non-cancer risks. Ecological impact on food webs. These are the type of long-terms that we address during this course. There are four main areas in the risk process. The risk analysis process is composed of identification, evaluation, communication, and control. Control is either by a regulatory body, a program, or a lawsuit. We will focus most of our attention on the identification and evaluation of chemical risk from emissions to the atmosphere. This is a more elaborate graph of the previous slide, where we will detail the evaluation phase on the risk analysis. We need to gather data. This is from the fleet of cars, the type of cars, the age of cars, the fuel type that these cars are burning, because the same car burning different fuels. Is it ethanol? Is it gasoline? Is it a mixture of ethanol and regular gasoline? The emissions phase, how much is being emitted. The fate and transport, including the atmospheric dispersion model, exposure analysis to both humans and ecological receptors, the dose, and then the health risks and ecological risks. So as a simplified view of this risk process, we start with the initiation. We gather data, conduct emissions inventory. Once that is done, we pass it to the fate and transport. That will include dispersion modeling of the products into the atmosphere, and then from the atmosphere to the various media. We will see a more complex view of this on the next slide. Exposure, both to human receptors and ecological receptors. A dose and a final risk. Now, the more complete view of this flowchart is here, where we specify emissions, need to know the fleet, the amount of miles traveled or kilometers traveled by these vehicles. What is the site? Need to know about topography, the use of the land, how rough it is. It is flat and white, or is it flat and dark soils? Or is it flat covered with houses or covered with trees? What is the road network? So need to know about the meteorology, for example. One aspect of the risk assessment that we must be aware is this. For many decades, cigarette companies fought lawsuits successfully because they could demand 100% certainty that smoking would cause cancer. To avoid this, the United Nations then, in the Rio Declaration in 1992, came up with a precautionary principle. And that states basically that if there is risk of serious threats and the damage is irreversible, the lack of full scientific certainty can never be used as reason for delaying any measures to prevent environmental degradation. And that's the reason that we are not going to call our air toxics or chemical that will cause cancer. We call them COPCs, and that stands for chemical of potential concern. And it goes beyond the 188 US EPA hazardous air pollutants, the HAPs. Any chemical may cause irreversible damage. We will call them a chemical of potential concern, COPC for short. Once we expose the atmosphere to these toxics, the atmosphere will transport them, but it will also transfer them to other media. They will transfer basically to water, to soils, to plants and animals. And we will have to investigate all those exposure pathways on our work. There are specific approaches, mathematical models that will be able to handle this. This is a more elaborate definition of the exposure pathway. Just here on the water, for example, there will be direct deposition of these chemicals to the water body, but there will be indirect loads to the water body by depositing on the watershed. And when it rains, it will wash some of that and bring those pollutants to the water body. And how are we exposed? Well, once the water body is loaded with chemicals, we can drink from reservoirs and we get contaminated, or we can eat fish that lives in the reservoir, contaminate the fish tissue, we eat that, we get contaminated. We will address all those as we have specific lectures for the fate and transport and exposure pathways. Those requires definition, and Paracelsus defined this well. The poison is based on the amount you consume, and this is our work. It is under our obligation to define what is the maximum amount we have before that chemical starts causing harm. And how does the chemical get to the body? Through intake and uptake. Intake is either we breathe that or we eat products that are contaminated. The term uptake is absorption through skin or eye. Once the chemical gets into the body, we're going to have these exposure to obtain the dose. Direct inhalation, oral, that would be eating contaminated food, for example, drinking contaminated water, and dermal contact. We have two other specific definitions and terminology that we need to be aware of. If we have chemicals dissolved in water, for example, and in air, how much will stay in the water, how much will stay in air. We need to define this. We have a Henry's law that will support our model. And we also have for all these chemicals, we will have the Henry's law constant. And when we are doing the mathematical part of this course, we will have to make use of Henry's law. The next important concept is this. We will transfer chemicals from soils, for example, to plant roots, from plants to animals. So we need to be able to evaluate chemicals, how they're going to go from media to media and how they are transferring. And We cannot measure 60,000 coefficients on all the things we need to do. So we have some estimations. There are some measurements, of a very few of them, but we need to estimate most of these properties, these transfer properties. And these use the famous octanol water partitioning coefficient. And what it is this. We mix octanol and water, and we put a chemical that is shaken or mixed within the mixture. And when the mixture separates, the water separates from the octanol, we will measure how much stays in the octanol part and how much will stay in the water part. This is very important because organic compounds will partition between the water and octanol. In the body, will partition between dissolve in the blood in the water portion and the lipids and other organic materials that we are composed of. The problem with the octanol water partitioning coefficient, the KOW, is that the ranges goes from 10 to the minus 3, 10 to the 7. So we never address them as the KOW directly. We talk about the log base 10 of KOW. And this way we have minus 3 to 7, and it makes it more manageable. Now I talk about how it transfers from soil to plant, from plant to animal. And it's the biotransfer factors we need that in our models. And as these factors will be tabulated, we have them in the document that I was one of the co-authors, the US EPA Human Health Risk Assessment Protocol. We will use this protocol in our course, and we define them by the acronym HHRAP. And here in this example, we have a feed that was contaminated. It has root uptake, direct deposition, absorption through air, and then cattle eats the feed. How much of the contamination in the feed we will actually get to beef tissue and to milk? And we account for that in part by having these biotransfer factors, the BF for milk, BF for beef. Once animals and humans eat and have intake, drink contaminated water, breathe them in, there are certain chemicals that will persist inside the body. And these persistent chemicals, they are usually lipophilic. And we need to understand how they bioaccumulate. We will cover that during the course. Let's consider this in a food web. Once the plant absorbs the contaminant, animal will eat that contaminant. Most of these contaminants, they're not like salt. The human body knows how to handle salt. We ingest salt and we get rid of salt. Some of the chemicals, we will not get rid of most of the chemical. It might bioaccumulate. Then as a herbivore eats plants, tissue gets concentrations that are higher than the plant. Now, when a carnivore eats the herbivore, the contamination in the carnivore will be higher than the herbivore. And this is biomagnification. The last topic I want to cover is based on allometric equation. We cannot contaminate 5,000 animals and then expose 5,000 not to contamination, and then we can evaluate both of them. It takes too long, costs too much money, there are just too many chemicals, thousands coming every year, and it costs a fortune. So we need to get cheap to test animals, for example, mouse. Certain amount of them, up to 5,000, can be contaminated, and then you have to have the control group with the same amount being not contaminated. The only difference in feed and exposure for each one of the animals is how much contamination of one specific chemical you provide. Now you need to then extrapolate what we get from this animal to other animals, from mouse to humans, from mouse to horses, from mouse to bears. We also do from chicken to other birds, from chicken to eagle, as an example. And you may think these don't work or are very crude approximation. But the reality is the approximations are fairly good. Strange enough, allometry, which is a study on how animals differ in terms of metabolism and other aspects, provides some very robust correlations. And I like to give this example because a mouse lives 2 years and the heart will pump about 2 million times. A blue whale, much larger mammal, will live 200 years and the heart will beat approximately the same amount, 2 million times. So that's it for this section, and we're done for lecture 1. Once more, if you have questions, please feel free to email me. Thank you very much.